when solving logarithmic equations, my approach is going to be very similar to exponential equations, and then I'm going to try to get the log by itself. And then I'll use the inverse of the logarithm, which is to, in effect, raise make each side of the equation an exponent of whatever the base of the logarithm is. So I'm going to try to get this logarithm by itself. So I'm going to start by adding 3 to both sides and get, how about, in getting 2 log base 5 x is equal 13. How about I divide everything by 2 and get log base 5 of x is equal to 13 halves. How do I undo this? Well, I like to think of it like this. I'm gonna make these expressions each the exponent of whatever this base is. So I'm going to think of this as 5 to the log base 5 of x, and that's equal to 5 to the 13 halves. Why do that? Well, because exponentials and logarithms are inverses, and if 5 to a log of that same base is going to undo on the left-hand side. This is going to give me x on the left-hand side, and this is going to give me 5 to the 13 halves power, or 5 to the 6.5. It's a fairly large number. I'll figure out what that is in my graph calculator. 5 to the 13 halves is 6.5, which is approximately 34938.6. Stick with the exact answer. Okay, how about this guy? How about add 4 to both sides? 2 natural logs of x is equal to 18. Natural log of x is equal to 9. So how do I undo natural log? Well, same as I did over here. I'm going to make this the exponent of the base, and the base of the natural log is e. E to the natural log of something is just whatever that inside is. That's equal to e to the 9th. Natural log base x of 500 plus 5 equals 8. Well, what is this? Well, how about I subtract 5 to start? Log base of some unknown base of 500 is equal to 3. If I wrote this in exponential form, that would be like saying x to the 3rd power is 500. And when I'm in exponential form, it's clear how to do here. I should take the cube root. Or another way to say is raise everything to the 1/3 power. So x is equal to the cube root of 500, which is the same as 500 to the 1/3 power, which is approximately 7.937. How about an expression that's a little more complicated? I think in this situation, if I could get these two, if I could get the same logarithm on each side with the same base, then if I have that going on, then if it's a single logarithm with the same base equal to another single logarithm with the same base, then I know the inputs are equal. So if I could get to that situation, then life would be good. So maybe I start by, let's see, property of logarithms. If I subtract logarithms, that's the same as the quotient of a single logarithm. And that's equal to natural log of x minus 3. That's good. I have the same logarithm with the same base. So if that's the case, then the inputs have to be equal. So this tells me that x plus 1 over x minus 2 is equal to x minus 3. How do I solve this? Well, maybe I throw a 1 under this guy, and I can cross multiply. So I get x plus 1 is equal to x minus 2 times x minus 3. I can multiply this out. X squared minus 2x minus 3x minus 5x plus 6 is equal to x plus 1. I can subtract x from both sides. Subtract 1 and get x squared minus 6x plus 5 equals 0. This factor, in fact it does, this factors to x minus 1 and x minus 5. So x equals 1 or x equals 5. It turns out that in fact both of these are not solutions, only one is. Only one of these solutions is valid in this original equation. If I plug in 1, I get natural log of 2 minus natural log of negative 1 equals the natural log of negative 2. And as we've seen time and time again, negative numbers are not in the domain of the logarithm function. So plugging in 1 makes a logarithm, one of the original problems, to have a negative logarithm. This is extraneous. 5, however, works perfectly fine. Natural log of 6 minus natural log of 4 equals the natural log of 3. Perfectly acceptable, nothing wrong with that. Life is good. So x equals 5 is our only solution. Let's try again. Let's see, I have two logs of the same base, so I can get log base 4 of x times x minus 1. That is equal to 1/2. I don't have two logs here, but maybe I could try how about I use my trick of raising to the power of, make these the exponent of whatever that base is. So maybe I'll try my trick of making this a 4 power 4, making that a power of 4. Those will undo, and I'm left with x times x minus 1, or x squared minus x, is equal to 4 to the 1/2 power, which is equal to 2. Or better yet, x squared minus x minus 2 equals 0. X minus 2, x plus 1 equals 0. So x is either equal to 2 or x equals minus 1. And again, going back to the beginning, if I plug in minus 1, I get log base 4 of minus 1, which is immediately not allowed. Plug in 2, log base 4 of 2, that's fine, plus log base 4 of 2 minus 1 is positive 1, that's fine, is equal to 1/2. All those fun games. X equals 2. Lastly, we can solve exponential function. Another technique for solving exponentials is by graphing. This should be your fallback method for solving any equation, let alone exponentials. But to solve by graphing, I'm going to graph left side, graph the right side, and then see where those things intersect. So I'm going to add a new graphing page. I'm going to type in the left-hand side, 3 times 2 to the 3x plus 5. I'm going to graph the line, the right-hand side, which is the horizontal line 65. I'm going to zoom out until I can see the intersection of these two graphs. There we go. And then I'm going to use my graph calculator to find the intersection. So I'm going to graph. When I show my work, or to show that you know what you're doing, I'm going to get a sketch of this graph. It does not have to be perfect. Does not need to be perfect. But the important information should be on here, which is what the graphs, a basic sketch of what the graphs more or less look like. Identifying the point of intersection, 1.441, 65. Thus the input that makes both sides 65, 1.441.